So in the sciences, we use stats to test our hypothesis, to tell us, is this true, is this not true, what's the probability of these two events happening at the same time. And it just helps us come up with our conclusions. When you're doing your hypothesis testing, the first thing you have to do is come up with the hypothesis. So you form a null hypothesis and an alternative hypothesis. We'll go through these in some examples in a little bit, but the null is basically saying, like, there's no difference between this group and that group. The alternative is saying there is a difference. Then you need to figure out which type of test to use. There's a whole bunch of different tests, from correlations, t-tests, ANOVAs, MANOVAs, whole lot of stuff out there. And then you need to calculate your test statistic. So are you going to use a t or an f or a chi-square, and figure out your degrees of freedom. And again, we'll go through these in a little bit. And then you figure out your critical value based on the test statistic you're using. Man, I'm having a hard time with that. Figuring out the test statistic you're using, your degrees of freedom, and your p-value. So what probability are you okay with being wrong? You find those in these statistical tables. There's one in your lab manual. Appendix 4 has a t-table for you. And then, based on that, you can either reject or fail to reject your null hypothesis. You do that by comparing your critical value to the value that you calculated. If your calculated value is bigger than your critical value, then you reject the null hypothesis, which means you accept the alternative hypothesis. So, first, a null hypothesis, basically saying there's no difference. Here are some examples. Male spiders, on average, are the same length as female spiders. Or the diameter of a tree is unrelated to its age. Antlion nests are distributed randomly, and then dandelions and clovers are not associated with each other. Possible alternative hypothesis, you see HO or H-OT is a short version of saying null hypothesis, while your alternative is H1. So the alternative for the spiders would be male spiders are not the same length as female spiders. Tree diameter is not positively related to age. Antlion nests are not distributed randomly, and then dandelions and clovers have no positive association with each other. If you notice these, like especially this one, male spiders are not the same length as female spiders. Well, those male spiders could be bigger, or they could be smaller. And so you can actually come up with more than one alternative hypothesis. You're always going to have one null. There is no difference. But then you can have multiple alternatives, and so you can see H1 and H2 are ways to write your alternatives. You can have H3, H4, H5, just as you start building up your alternative hypotheses. So the males could be larger than the females, or the males could be smaller than the females. When you want to figure out which test statistic to use, you need to figure out what you're testing. So if you want to look at the difference between two means, you'll just use a t-test. Student t-test, really one of the most common types of statistical tests that's done, just comparing the means of this sample and that sample, these two groups. If you want to look about a bunch of different stuff, you'll use an ANOVA or an F-test. The F-tests are things like ANOVAs, MANOVAs, whatever. If you want to look for correlation, you'll run a correlation. A lot of correlations can be like types of regressions. Test the dispersion, you can use a modified t-test. Test for association, you'll use a chi-square. And then test of independence, trying to figure out if this thing is dependent on this thing, you can use also a chi-square. Figuring out which test statistic to use, for me at least, is like one of the harder things to do. But after you figure out your test statistic, then you want to figure out your degrees of freedom. So we know what we're going to use. if you're using a t-test, you want to use a t value, ANOVA and F, a chi-square, a chi value, right? Your degrees of freedom are either going to be n minus 2, n minus 1, or your row minus 1 versus your column minus 1. You'll see this a lot, like in your ANOVAs, also your correlations. So, we have our degrees of freedom. We know which test we're using. We know the stat that we're going to use for it. Now we need to calculate our critical value. You'll use a statistical table like in Appendix 4, and you'll look for your p-value that you are going to be okay with having. Those are always going to be at the top of the table, and then your degrees of freedom are going to be down the side as your rows. Okay, so you have a degree of freedom 2, a p-value of 0.4, you just match them up, and that value is going to be your critical value. Like, so using stats, this is just a way to take like a whole bunch of messy data and try to make sense out of it. So, you know, when we were looking at male spiders versus female spiders, if we just grab 10 males, 10 females, we could, just based on random chance, grab 10 male spiders that are really big and 10 female spiders that are really small. And when we measure them up against each other, it looks like there's no difference. And that can happen, right? There's a possibility of that. So even if you end up with like an outrageous t-value or whatever, like there could be a chance based on just random chance that these two spiders typically won't be this, but based on what you pulled, that's what it turns out to be. In a lot of scientific studies, we use a p of 0.05 as our cutoff point. Like, okay, 0.05 or lower, we're saying these two things are significantly different from each other. 0.05 means 5% of the time we could be wrong. So that's saying like 1 out of 20, we could be wrong, right? Maybe there is not a difference between them. We don't know, right? And so the p-value is just for probability. What is the chance that these things are similar or not similar? So is it okay to always use a p of 0.05 as your cutoff? Well, what if you're giving humans a medicine and it kills 1 out of every 20 people? Probably want to use a p that's a little bit stricter than that. So like a p of 0.001 or 0.00001. Like, so it depends on what you're testing and what you're comfortable with being wrong at. Typically, in a lot of our studies, it's 0.05. Alright. So, we have our critical value. Then we just reject or fail to reject the null hypothesis. If your p is larger than 0.05, you fail to reject your null hypothesis, which means you're accepting your null hypothesis. You're saying there is no difference between this group and that group. If you reject the null hypothesis, you're accepting your alternative hypothesis, saying that there is a difference between this group and that group. So in our example with our spiders, say the spider example, we calculated a t-value of 3.18. The critical for that would be 2.28. And turns out that our t calculated is larger than our t critical, and so we reject the null hypothesis. We're saying that these two groups are not the same. When you do a bunch of stats, there's a whole bunch of assumptions that go with them. and rarely are you going to have your data match all the assumptions perfectly. And so a lot of times statisticians or scientists will transform their data to fit the assumptions for stats. Like all your tests say that you need to have a normal distribution, so a nice little normal curve, no heteroscedasticity, no collinearity, like a whole bunch of terms you don't need to know in this course, because the tests that we're doing with the data that we're going to gather, like our tests are really robust. Like they can handle not meeting all these assumptions and still be true, still give us reliable data. So using a t-test to test the differences between the means is what we're going to work on in the next video.